Hi guys and welcome back. My name is Abyaz Attaqee Shah Oktora and this is the fourth video on my series about the class Wireless Communication and Convergence Network. This video will summarize the contents of the fourth week's lecture, which is titled Wireless Communication. So let's go straight to my summary of the lecture. We are going to first talk about the history of wireless communication. So the first wireless networks were developed in antiquity. These systems transmitted information visually over line of sight distances, later extended by telescopes, using smoke signals, torch signaling, flashing mirrors, signal flares, or semaphore flags. An elaborate set of signal combinations was developed to convey complex messages with these rudimentary signals. Observation stations were built on hilltops and along roads to relay these messages over large distances. These early communication networks were replaced first by the telegraph network, invented by Samuel Morse in 1838, and later by the telephone. The origins of radio communications began around 1820, with experiments by Ørsted demonstrating that an electric field could move a compass needle, thereby establishing a connection between electricity and magnetism. Works by Ampere, Gauss, Henry, Faraday, and others further advanced knowledge about electromagnetic waves, culminating in Maxwell's theory of electromagnetism, published in 1865. The first transmission of electromagnetic waves was performed by Hertz in the late 1880s, after which he famously declared to his students that these waves would be of no use whatsoever. He was proved wrong in 1895 when Marconi demonstrated the first radio transmission across his father's estate in Bologna. This moment in history is considered the birth of radio communications. Marconi then moved to England to continue his experiments over increasingly large transmission ranges, culminating in the first transatlantic radio transmission in 1901. After that, in the 1940s, many sophisticated military radio systems were developed, while in 1988, the exponential growth in cellular use happened. And then, finally, at present times, in where Wi-Fi is enjoying tremendous success and growth, combined with widespread use of Bluetooth and satellites. That concludes the history of wireless communications. Now we are going to go to the next part, which is going to briefly talk about the future of wireless networks. So future wireless networks is imagined to be ubiquitous communication among people and devices. It is also expected to be able to support machine-to-machine communications for tens of billions of devices. Some examples of those are next-gen cellular or Wi-Fi, smart homes or spaces, autonomous cars, smart cities, body area networks, Internet of Things, and many, many more. Now we are going to talk about the types of challenges that is facing wireless networks. So there are two types. The first is network and the second is device. So first we are going to talk about the network challenges. First is data rates with no errors. Second is energy efficiency. Third is scarce/bifurcated spectrum. Fourth is reliability and coverage. Fifth is heterogeneous networks. And sixth is seamless internet work handoff. For the device part of the challenges, the first is performance, second is complexity, third is size, power, cost, and energy, fourth is high frequencies, fifth is multiple antennas, sixth is multi-radio integration, and seventh is coexistence. After hearing about all these different types of challenges that is facing wireless networks, we might be wondering what are some of the solutions that we can use to try to solve these challenges. So the first of these solutions might be solutions is called a software defined radio, or SD radio, for the device challenges. So it is a wideband antenna with analog to digital converters spanning the bandwidth of desired signals, with the digital signal processor programmed to process desired signals. So nowadays, this is not cost, size, or power efficient. With the challenges out of the way for wireless communications, now we are going to do a bit of a detour to talk about Internet of Things. So, what is Internet of Things? So, Internet of Things describes physical objects or groups of such objects like these uh, that are embedded with sensors, processing ability, software, and other technologies that connect and exchange data with other devices and systems over the internet or network or other communications network. So this picture here is an example of how an IoT might work. Okay, so that's just a quick detour to explain about Internet of Things. Now we are going to talk about Shannon's limit, or Shannon's theorem. In information theory, the noisy channel coding theorem, sometimes referred to as Shannon's theorem or Shannon's limit, establishes that for any given degree of noise contamination of a communication channel, it is possible to communicate discrete data, digital information, nearly error-free up to a computable maximum rate through the channel. This result was presented by Claude Shannon in 1948 and was based in part on earlier works like ideas from Harry Nyquist and Ralph Hartley. So, the Shannon limit or Shannon capacity of a communication channel refers to the maximum rate of error-free data that can theoretically be transferred over the channel if the link is subject to random data transmission errors for a particular noise level. It was first described by Shannon in 1948, as I said, and shortly after published in a book by Shannon and Warren Weaver entitled The Mathematical Theory of Communications in 1949. This founded the modern discipline of information theory. There are two major opinions that came up when we are discussing about Shannon's limit. So the first is we are at Shannon's limit. The second is Shannon was wrong, there is no limit. So what would Shannon say? We don't know. The fact is, we don't know the Shannon capacity of most wireless channels. For example, like in time-varying channels, channels with interference or relays, cellular systems, ad hoc and sensor networks, or channels with delays. So what the Shannon theory provides are design insights and the upper limits of system performance. So that ends our bit of explanation about the Shannon's limit. Now we are going to talk about the comparison between current and next-gen wireless systems. So for current, the telltale signs are 4G cellular systems, 6G wireless LANs/Wi-Fi, 802.11ax to be exact, and we also have wave with massive MIMO systems. MIMO is multi-input, multi-output systems, satellite systems, Bluetooth, Zigbee. This is for you who likes to tinker with Arduino, you probably have heard of this, and WiGig. And for the emerging wireless systems, we have 5G cellular and 7G Wi-Fi systems, ad hoc and cognitive radio networks, energy harvesting systems, and even in the chemical/molecular side of things. In short, there is much room for innovation. With that out of the way, now we are going to do a bit of a sidestep, and now we are going to talk about spectral reuse. So, due to its scarcity, spectrum is reused. For example, like in license bands, in which the system is divided in cellular, or in unlicensed band, like in, for example, the most common is Wi-Fi. So, first we're going to talk about cellular system. which is reuse channels to maximize capacity. So the geographic region is divided into cells with time slots reused in different cells. The interference between cells using same channel, it is mitigated using a interference mitigation key. And it also has base stations slash MTSOs to coordinate handoff and control functions, basically like a home hub of the cellular system. And there's also an added option in which if we shrink the cell size, we can increase the capacity for the system itself. So that is a short explanation about the cellular system for license bands. So now we are going to go and talk about 4G slash LTE cellular. Sorry there, with a bit of editing magic, I corrected some mistakes that I made in the slides. So now we're going to talk about 4G slash LTE cellular. So there are some features that are prominent in 4G cellular systems for cellular networks that differentiates it from 3G networks or older systems. So the first is much higher data rates than 3G. So 50 to 100 megabytes per second. Usually 3G systems has 384 kilobytes per second peak rates. The second is greater spectral efficiency. So it has more bandwidth, it has an adaptive OFDM MIMO, and also it has reduced interference. Third is the flexible use of up to 100 MHz of spectrum. So 10 to 20 MHz spectrum allocation is common. Fourth is low packet latency, under 5 milliseconds. Six is reduced cost per bit, which is not clear to consumers, but it's always good to have. And it also has an all IP network. Sorry about that. So that is all about 4G slash LTE cellular. Now we are going to talk about what what is upgraded when we go from 4G to 5G. So the first is extreme mobile broadband. So 5G brings 5G not brings, but 5G has over 10 gigabytes per second peak data rates. It has 100 megabytes per second available 24/7 and supporting way more traffic than in 4G. The second is critical machine communication. So with less than 1 millisecond latency and is super reliable. The third is massive machine communication, in which with a super low cost of machine-to-machine connection, significantly longer lifetime, and supporting hundreds of machines connected at the same time. Moving on now, we are going to talk about Wi-Fi networks, which brings multimedia everywhere but without wires. So here in this picture, here is an example of how a Wi-Fi network might look inside a house. So it basically enables you to stream content or videos and has access to gigabytes per second data rates, has a high reliability, and it also provides you with coverage inside and outside the house itself, because as if you see clearly here, and the range of the Wi-Fi network does not it does not get blocked by walls. So even if you are outside of the room where the router itself is placed, you can still get the coverage, you can still get the Wi-Fi network. Speaking of Wi-Fi networks, we are going to talk a bit more about wireless LAN standards. So over the course of WLAN history, we have three different stages of standards for WLAN. The first is the old, from the 1990s, 802.11b. It has a standard for 2.4 gigahertz ISM band. It is a direct sequence spread spectrum, or DSSS, and it has speeds of 11 megabytes per second with an approximate range of 500 feet. The second stage of WLAN standards is the middle age. 802.11a/g. It it spans from the middle age. It spans from mid to late 1990s. So the standard for a 5 gigahertz band, 300 megahertz, it's also 2.4 gigahertz, and it also has an OFDM in 20 megahertz with adaptive rates, and it has speeds of 554 megabytes per second with an approximate range of 100 to 200 feet. So between these two different stage standards, there are many different WLAN cards generations. So now we're going to go to the last stage of the WLAN standards, which is 802.11n/AC/AX or Wi-Fi 6, which is the current generation. It is standard in 2.4 gigahertz too, and a 5 gigahertz band. It is adaptive OFDM/MIMO in 20, 40, 80, and 160 megahertz. It has 2 to 4 antennas. It could also be up to 8. It also has speeds up to 1 gigabyte per second with an approximate range of 200 feet, while also having other advances in packetization, antenna use, and also a multi-user MIMO. Now, after speaking about WLAN standards, we are going to talk about Wi-Fi performance. So, what are the possible reasons Wi-Fi performance can suck? So, because we're talking about Wi-Fi standard in the last part, from that point of view, the Wi-Fi standard lacks good mechanisms to mitigate interference, especially in areas with many different APs. APs stands for access points. So to combat that, we have a solution that is called self-organizing networks for Wi-Fi, or SON. The SON controller is used for channel selection, power control, and etc. It is a dynamic self-organization network software to manage Wi-Fi's APs. It allows for capacity/coverage/interference mitigation trade-offs, and it provides network analytics and planning. Now that wraps up the Wi-Fi part of the lecture. So now we are going to talk about the next part, which is about satellite systems. Satellites, they cover a very large area. They also have different orbit heights. So the orbit height trades off coverage area for latency. So the main three orbit heights that satellites have are GEO, or geostationary orbit, around 39,000 kilometers above the Earth's surface, and MEO, medium Earth orbit, which is 9,000 kilometers above the Earth's surface, and LEO, or low Earth orbit, which is 2,000 kilometers above the Earth's surface. It is usually optimized for one-way transmission. For example, radio and movie broadcasts. Most two-way LEO systems went bankrupt in the 1990s to 2000s, but LEOs have resurfaced with 4G to bridge digital divide. It is also used as the backbone for the GPS, or the Global Positioning System. Satellite signals used to pinpoint locations, and it is popular in cell phones, PDAs, and navigation devices. That is all for the satellite systems, and now we are going to move on to Bluetooth. It is originally designed as a cable replacement, a low cost, and it still has a short range, 10 meters, but it is extendable to 100 meters. It uses a 2.4 gigahertz band, and it is widely supported by telecommunication, PC, and consumer electronic companies. Now, with that short explanation of Bluetooth, we are going to quickly move on, a bit of a detour again, to spectrum regulation. So spectrum is a scarce public resource which means that it needs to be allocated. So in the US, for example, it is controlled by the FCC for commercial use or the OSM for defense use, for military usage. And FCC auctions spectral blocks for set applications. So if a service wants to use a spectrum, then they need to join the auction, the FCC auction, and to purchase the spectrum block for their set of applications. So some spectrum set is is set aside for universal use, so for anybody can use it. For worldwide spectrum, it is controlled by the ITUR. And finally, we are going to talk about emerging systems. Systems that might come up in the future that is connected to wireless networks. Some examples are new cellular system architectures, waves / massive MIMO communications, software-defined network architectures, ad hoc / mesh wireless networks, cognitive radio networks, wireless sensor networks, energy constrained radios, distributed control networks, chemical communications, and finally applications of communications in health, biomedicine, and neuroscience. So now it's the time to show you a summary of the summary for this lecture. I guess the main points. So the wireless vision encompasses many exciting applications. The technical challenges transcends all system design layers. 5G networks must support higher performance for some users, extreme energy efficiency and or lower latency for others, cloud-based software to dynamically control and optimize wireless networks, innovative wireless design needed for 5G, cellular / Wi-Fi, wave systems, and massive MIMO and IoT connectivity, and standards and spectral allocation heavily impacts the evolution of wireless technology. So that is it for my video of summarizing this fourth lecture for my class. Sorry if I made some mistakes. Thank you guys for listening and see you guys on the next video. Bye bye.